What does it mean when a comet acts alive? Not metaphorically, not poetically, but literally emitting water where water should be frozen solid, behaving in ways that violate every model we have. This is not a riddle. This is not science fiction. This is happening right now in the outer solar system, and it has astronomers whispering a word they almost never use: impossible. The object is called 3I Atlas. The 3I means it's the third confirmed interstellar visitor to our solar system, a traveler from another star, passing through our neighborhood on a journey that began long before humans existed. It was discovered by the Atlas Survey System, a network of robotic telescopes designed to scan the sky for anything unusual: asteroids, comets, near-Earth threats. They found something unusual. At first, 3I Atlas seemed ordinary enough, a faint smudge of light moving slowly against the background stars. Its trajectory was hyperbolic, the hallmark of an interstellar object, unbound by the sun's gravity, destined to leave our solar system forever. Astronomers calculated its path, logged its brightness, and prepared to watch it fade as it continued outward into the dark. But then, the comet switched on. Not gradually. Not in the slow, predictable way that comets brighten as they approach the sun. This was abrupt, sudden, as if someone had flipped a switch. 1 week the comet was inert cold, dark nucleus reflecting only sunlight. The next week it was surrounded by a glowing cloud of gas, a coma stretching tens of thousands of kilometers into space. And the data showed something extraordinary: water. Massive amounts of water vapor, 40 kilograms per second. That's 1.35 times 10 to the 27th molecules escaping into space every second. Picture a fire hose wide open, pouring water into the void, except the hose never runs dry, and the source is a block of ice smaller than a city. That's already unusual. But here's the impossible part. 3I Atlas is 3.5 astronomical units from the sun. That's 3.5 times the distance between Earth and the sun. Out here, sunlight is weak, faint. The solar energy reaching this comet is less than 8% of what we receive on Earth. At this distance, water ice should be dormant, locked, frozen solid like permafrost in the Arctic winter. Think of it this way. Imagine placing a block of ice in your freezer. Now imagine moving that freezer to the far end of a football field and lighting a single birthday candle at the opposite end. The ice shouldn't melt. There isn't enough heat, the distance is too great, the physics doesn't allow it. And yet the ice is melting. Not just melting, boiling, vaporizing, pouring steam into the air at a rate that makes no sense. That's what 3I Atlas is doing. The Swift UV telescope detected it first. Hydroxyl radicals OH molecules, the chemical fingerprint of water breaking apart under ultraviolet light, formed a halo around the nucleus. The spectral lines were clean, unmistakable: water vapor, active, continuous, impossible. Astronomers recalibrated their instruments, checked the data pipelines, ran the numbers again. The signal persisted, 40 kilograms per second. Day after day, week after week, the comet kept breathing. The Very Large Telescope in Chile confirmed it. Gaia, the European Space Agency's astrometry satellite, tracked the comet's changing brightness. LOFAR, the low-frequency array in the Netherlands, detected faint radio emissions consistent. With active outgassing, every instrument told the same story: water, distance, impossibility. No comet should behave this way. The energy budget doesn't work. The temperature models fail. The standard physics of cometary sublimation, tested and refined over decades, verified on hundreds of comets, predicts dormancy at 3.5 AU. Not silence, not stillness, but certainly not this. And yet, here we are. There are no contradictions in the data, no instrument errors, no calibration mistakes. The comet is real. The water is real. The distance is real. What isn't real, what doesn't fit, is the explanation. Because if sunlight alone can't drive this activity, something else must. But the question remains: what? Comets are ancient, frozen time capsules from the birth of the solar system, 4.6 billion years ago, when the sun was young and the planets were still forming. They are made of ice-water ice, mostly, mixed with frozen carbon dioxide, carbon monoxide, methane, ammonia. Dust. Rock. Organic. Molecules. The leftover debris of creation, preserved in the deep freeze of the outer solar system. When a comet approaches the sun, it warms. The surface heats. Subsurface ices begin to sublimate, to transform directly from solid to gas without melting. The gas escapes through cracks and pores in the nucleus, carrying dust with it. This creates the coma, the glowing cloud that surrounds the nucleus, and sometimes a tail, that iconic streak of light, stretching millions of kilometers across space, always pointing away from the sun. This process is well understood, predictable. At 1 AU Earth's distance from the sun, water, ice sublimates vigorously. The solar flux is strong enough to drive continuous outgassing. At 2 AU, activity drops. The sunlight is weaker. Sublimation slows. At 3 AU, most comets are barely active. At 3.5 AU, they're dormant. This is not opinion. This is measurement. Decades of observations. Hundreds of comets. The relationship between solar distance and cometary activity is one of the most reliable patterns in planetary science. 3I Atlas is not following the pattern. Spectroscopic data from the Very Large Telescope reveals the chemical composition of the coma. Water vapor, yes, but also carbon dioxide in staggering quantities. The CO2 to H2O ratio is roughly 95:5. That's backwards. In most comets, water dominates. Carbon dioxide is a minor component, a supporting actor. Here, the roles are reversed. Carbon dioxide is more volatile than water. It sublimates at lower temperatures farther from the sun. Its presence at 3.5 AU is not surprising. What's surprising is the water. CO2 should be driving the show. Water should be absent, or nearly so. Instead, we're seeing both CO2 in abundance and water at rates that defy explanation. This is smoke without fire, footprints without feet. One hypothesis emerged quickly: hypervolatile ices. Perhaps the nucleus contains pockets of carbon monoxide or nitrogen ice buried beneath the surface. These substances sublimate at extremely low temperatures, far below the threshold for water ice. As they escape, they could fracture the overlying layers, exposing deeper water ice to sunlight or vacuum. The escaping CO or N2 could drag water molecules along, creating the observed outflow. It's an elegant explanation, reasonable, testable, but it has a problem. If hypervolatile ices were driving the activity, the outburst would be transient, temporary. CO and N2 reservoirs are finite. They sublimate quickly. Within days or weeks, the hypervolatile pockets would empty, the fractures would close, and the comet would go dormant again. 3I Atlas has been active for months. The water emission began in early spring. By midsummer, it had not diminished. By autumn, it continued unabated, 40 kilograms per second. Steady, relentless, as if the comet had access to an inexhaustible reservoir of energy, a hidden furnace warming the nucleus from within. But there is no hidden furnace. Comets don't generate internal heat. They're too small. They don't have radioactive cores like planets. They don't have tidal heating like Jupiter's moon Io. They're cold, inert, dead in the thermal sense. The only energy source available to a comet is sunlight, and sunlight at 3.5 AU is not enough. Alan Fitzsimmons, an astronomer at Queen's University Belfast, who has studied interstellar comets extensively, once remarked that the behavior of these objects challenges our assumptions. That's the language scientists use when they mean, we don't understand this. The models don't work. The energy doesn't balance. The water shouldn't be there. And yet, it is. Imagine standing in the desert at noon. The sun is blazing. The air is hot. You're sweating. Now imagine that same desert at midnight under a moonless sky. The temperature has plummeted. The air is cold. You're shivering, but somehow, impossibly, you're still sweating, still losing water at the same rate as if the sun were overhead. That's what 3I Atlas is doing. It's sweating in the cold. It's exhaling water where water should be locked solid. It's violating the rules we thought we knew. and that's what keeps astronomers up at night. Then came the spectral lines that made no sense. Every comet carries a chemical signature, a fingerprint written in light. When molecules in the coma absorb or emit specific wavelengths of sunlight, they create patterns in the spectrum. These patterns tell us what the comet is made of: sodium, calcium, carbon, oxygen, iron, nickel, iron and nickel. These two elements almost always appear together, in meteorites, in asteroids, in planetary cores. They're cosmically linked, forged together in the hearts of dying stars, expelled in supernova explosions, mixed into the molecular clouds that birth new solar systems. When you find iron, you find nickel. When you find nickel, you find iron. The ratio varies, but the relationship holds. It's one of the most reliable patterns in cosmochemistry. 3I Atlas breaks the pattern. Spectroscopic observations from the Very Large Telescope detected nickel emission lines in the coma. Strong lines, unmistakable. Nickel atoms, glowing in the ultraviolet, scattered throughout the cloud of gas surrounding the nucleus. Iron, absent, not diminished, not trace, absent. The spectral lines that should accompany nickel-iron emission at specific wavelengths were missing. The ratio of nickel to iron was not skewed. It was infinite. Nickel without iron. A violation of cosmic chemistry. At first, astronomers suspected an observational artifact. Perhaps the iron lines were too faint to detect. Perhaps atmospheric absorption was masking the signal. Perhaps the spectral resolution wasn't high enough to resolve the features. They checked, recalibrated, observed again. The nickel persisted. The iron did not appear. Think of it this way. Imagine finding a beach covered in left shoes. Thousands of them. Different sizes, different styles, all left shoes. No right. Shoes anywhere. Not hidden, not buried, just absent. That's not how shoes are manufactured. That's not how they're distributed. Something strange happened to separate them. That's what 3I Atlas is showing us. Nickel without iron. A chemical asymmetry that shouldn't exist. One explanation: selective sublimation. Perhaps iron and nickel are bound in different compounds within the nucleus. Perhaps the iron is locked in refractory mineral silicates, oxides that require higher temperatures to vaporize. Nickel, on the other hand, might be present in more volatile compounds, carbonyls. Perhaps that's sublimate at lower temperatures. It's possible, but it requires a very specific set of conditions, a very unusual chemistry, and it still doesn't explain the water. Another explanation: the comet's origin. Perhaps 3I Atlas didn't form in a typical protoplanetary disk. Perhaps it condensed in an environment with unusual elemental abundances, a molecular cloud enriched in nickel, depleted in iron, or a region contaminated by a nearby supernova that altered the local chemistry. This would make 3I Atlas not just an interstellar visitor, but a visitor from a profoundly alien stellar nursery, a place where the rules of chemistry are different, where the cosmic mix of elements doesn't match our own. Or perhaps, and this is where the speculation begins, the nickel is not natural, not in the sense of artificial, not manufactured, but concentrated, processed, sorted, by some mechanism we don't yet understand. A mechanism that doesn't exist in our solar system. A mechanism that belongs to another star, another history, another set of physical processes we've never encountered. This is where science edges into mystery. The data is clear. The nickel is real. The absence of iron is real. The explanation is not. We'll return to this anomaly later. But for now, the question lingers. What kind of place produces nickel without iron? And what does that tell us about where 3I Atlas came from? Every object in the solar system has a story written in its orbit. The path an object follows through space, its trajectory, its velocity, its inclination, reveals where it came from and where it's going. Planets move in ellipses, bound to the sun by gravity, returning again and again in predictable cycles. Asteroids and comets follow similar paths, though more eccentric, more elongated. But some trajectories are different. Some are hyperbolic open curves that never close, paths that lead in from infinity and back out again. These are the trajectories of exile, objects not bound to the sun, visitors, interlopers, travelers from other stars. 3I Atlas follows a hyperbolic trajectory. Gaia, the European Space Agency's astrometry satellite, tracked the comet's motion with exquisite precision. The position, the velocity, the acceleration. From these measurements, astronomers calculated the orbital elements, the numbers that define the comet's path through space. The eccentricity, 1.03. Any eccentricity. Greater than 1 means the orbit is unbound. The comet will not return. It will not loop around the sun and come back. It is passing through once, and then it will leave forever. The inclination, 47 degrees. The comet's orbit is tilted sharply relative to the plane of the solar system, the flat disk where planets orbit. This is unusual. Objects born in our solar system tend to move in or near the plane. High inclinations suggest external origins. The velocity, 31 kilometers per second, relative to the sun. That's faster than any planet, faster than most comets. But not impossibly fast. Not so fast that it couldn't have originated within the Milky Way. Astronomers traced the trajectory backward. Where did 3I Atlas come from? What direction in space did it approach from? The answer, Coma Berenices, a faint constellation in the northern sky. The comet came from the direction of the galactic thick disk region of older stars, farther from the galactic plane, enriched in heavy elements. The thick disk is ancient. Its stars are 7 billion years old or more. They formed when the Milky Way was young, before the thin disk, the flat, star-rich plane where our sun resides, had fully settled. The chemistry of the thick disk is different. The stellar populations are different. The history is different. If 3I Atlas originated in the thick disk, it could be extraordinarily old. Older than our solar system. Older than Earth. A relic from the early Milky Way, wandering the galaxy for billions of years, finally stumbling into our sun's gravitational influence by sheer chance. This would make it not just an interstellar comet, but an ancient one, a fossil, a remnant of a stellar system that may no longer exist, a star long dead, its planets dispersed, its comets cast into the galaxy like seeds on the wind. But there's another possibility, one that's harder to test, harder to prove. Perhaps 3I Atlas didn't originate in the Milky Way at all. Galactic thick disk trajectories are consistent with local origins, comets ejected from nearby star systems, wandering the solar neighborhood. But they're also consistent with extragalactic origins. A comet from another galaxy, passing through the Milky Way, could enter our solar system from almost any direction. The thick disk trajectory might be a coincidence, a random intersection. There's no way to know. Not yet, not without more data. The velocity is too ambiguous. The trajectory is too generic. The chemistry, the nickel, the water. The CO2I is unusual but not diagnostic. It doesn't point uniquely to one origin over another. And so we're left with possibilities. The comet could be from the thick disk. It could be from the thin disk. It could be from a distant star cluster. It could, in principle, be from another galaxy, entirely Andromeda perhaps, or a dwarf galaxy long since consumed by the Milky Way. We don't know. And that uncertainty is itself unsettling. Because if we don't know where it came from, we don't know. What else is out there? How many other objects like this are wandering the galaxy? How many have passed through our solar system unnoticed? How many are approaching now, invisible, undetected, carrying chemistries and behaviors we've never seen? The universe is full of exiles. 3I Atlas is just the one we happen to notice. But the question remains, why did we notice this one? What made it visible? What made it active? And why now? Comets don't switch on. They brighten gradually as they approach, the sun warming slowly, sublimating incrementally. The transition from dormancy to activity is smooth, predictable, a curve on a graph rising steadily as solar distance decreases. 3I Atlas did not follow the curve. The Atlas survey telescopes photographed the comet every few nights as part of their automated sky patrol. In late winter, the images showed a faint point of light stellar in appearance, no visible coma, no sign of outgassing. The comet was inert, a dark nucleus reflecting sunlight, nothing more. 3 weeks later, the comet had a coma, not a faint haze, a fully developed cloud of gas and dust, tens of thousands of kilometers across, bright enough to be visible in amateur telescopes. The transition happened in days, perhaps less. The exact timing is uncertain because the survey telescopes don't photograph the same patch of sky every night, but the window is narrow. One observation, dormant. Next observation, active. The comet switched on. This is not normal. Comets can have outbursts, sudden, temporary increases in activity caused by subsurface ice pockets rupturing and venting gas. But outbursts are brief. They last hours or days. The brightness spikes and then fades. The comet returns to its previous state. 3I Atlas did not return to its previous state. The activity persisted. The coma remained. The water emission continued, week after week, month after month. Something triggered the switch. Something changed. One hypothesis, rotational state. Perhaps the comet was tumbling in a particular orientation that kept volatile-rich regions in shadow. As the comet rotated or as its spin axis shifted due to outgassing turquoise, these regions became sunlit. The ices warmed. Sublimation began. The comet activated. It's plausible. Comets are irregularly shaped. Their rotation can be complex, tumbling, precessing, chaotic. Small changes in orientation can expose different surface regions to sunlight, triggering sudden changes in activity. But this doesn't explain the persistence. If rotation were the only factor, the comet should deactivate again as the volatile regions rotate back into shadow. The activity should be periodic, cyclic. It's not. It's continuous. Another hypothesis, subsurface structure. Perhaps the nucleus has a thick, insulating crustal layer of dust and refractory material, covering the ices beneath. As the comet warmed slowly over weeks or months, heat conducted through the crust. When the subsurface temperature reached the sublimation threshold, the ices began to vent. The escaping gas fractured the crust. The fractures widened. The outgassing accelerated. The comet switched on. This is more consistent with the observations. Once the crust is breached, the ices are exposed. Sublimation continues as long as sunlight reaches the surface. The activity doesn't depend on rotation, it depends on exposure. But there's a problem. If the crust was thick enough to insulate the ices until the comet reached 3.5 AU, it should still be thick enough to insulate them now. The solar flux hasn't changed significantly. The temperature hasn't risen dramatically. What triggered the breach? Perhaps a crack already existed, a fissure, a weak point. Heat conducted through slowly, warmed a pocket of hypervolatile ice core, N2, which sublimated explosively, blowing open the crack. Water ice, now exposed, began sublimating. The process became self-sustaining. This is the best explanation we have. It's consistent with the observations. It's consistent with the chemistry. It's consistent with the timing. But it's not satisfying, because it requires a very specific sequence of events. A crack in the right place, hypervolatile ice in the right pocket, warming at the right rate. Too many coincidences. And it still doesn't explain the nickel. The switch is a pivot point. Before, dormant, invisible, unremarkable. After, active, glowing, impossible. Something fundamental changed, not just in the comet's brightness, but in its behavior, in its chemistry, in the way it interacts with sunlight. This is where the rules break, this is where our models fail, this is where the mystery deepens. Because if a comet can switch on suddenly without warning, violating every expectation we have, what else can it do? And that's what keeps astronomers up at night. The coma is not just water. It's a chemical library, a collection of molecules released from the nucleus, each one a clue to the comet's composition and history. Spectrographs break the light from the coma into its component wavelengths, revealing the molecular fingerprints hidden within. Water vapor, carbon dioxide, carbon monoxide, expected, and then cyanide. Not hydrogen cyanide gas, though that's present too, but cyanogen CN radicals, molecular fragments consisting of one carbon atom bonded to one nitrogen atom. These radicals glow in the ultraviolet and visible spectrum, producing distinctive emission bands. The Very Large Telescope detected them clearly. Cyanide is not unusual in comets. It's a common product of organic chemistry in the cold depths of space. Many comets carry it. Halley's Comet, perhaps the most famous comet in history, was rich in cyanogen when it passed through the inner solar system in 1910. The public panicked. Newspapers warned that Earth would pass through the comet's tail, that cyanide gas would poison the atmosphere. It didn't. The concentration was far too low. The panic was unfounded. But the presence of cyanide in comets is real. And it tells us something important. Comets contain organic molecules, complex carbon-nitrogen compounds, the building blocks of life, or at least the chemistry that could lead to life. In 3I Atlas, the cyanogen emission is strong, persistent, and it follows a pattern. The CN emission intensified several days after the water emission spiked, not simultaneously, sequentially. First water, then carbon dioxide, then cyanogen. As if the comet were releasing its inventory in layers, exposing the surface first, then deeper layers, then deeper still. This is consistent with the subsurface breach hypothesis. A crust fractures. Surface ices sublimate first water, the most abundant ice. Then the fracture widens, exposing deeper layers enriched in CO2, then deeper still, where organic ice's frozen cyanogen precursors begin to sublimate. The sequence suggests structure, layers, differentiation. The nucleus is not a homogeneous blob of ice and dust. It's stratified, organized, as if the comet formed in stages, accreting material under changing conditions, or as if it experienced processing, heating, alteration, something that sorted the ices by volatility, by composition, by chemistry. But comets don't process themselves. They're cold, inert. They preserve the conditions of their formation like fossils in stone. If 3I Atlas is stratified, that stratification happened somewhere else, in another star system, in another disk, in an environment we can't observe directly. The cyanogen raises another question. How much organic material does this comet contain, and what kind? Earth's oceans contain water delivered by comets and asteroids in the early solar system. The organic molecules in those impacts may have seeded the chemistry that led to life. If 3I Atlas carries a similar cargo water organics, cyanogen then, it represents a sample of another star's delivery system, the chemistry that built another world, or could have, but we can't study it up close. We can't send a spacecraft. 3I Atlas is already leaving. By the time a probe could reach it, the comet would be too far, too cold, too faint. The window of observation is narrow. Months, perhaps a year, and then it's gone forever. This is the frustration of interstellar objects. They appear without warning. We study them frantically, extracting every photon, every spectral line, every scrap of data. And then they vanish. Back into the dark, back into the galaxy. We're left with fragments, hints, questions, without answers. The cyanogen tells us the comet is chemically rich, complex, differentiated, but it doesn't tell us why it's active. It doesn't tell us where the energy is coming from. It doesn't tell us how water sublimates at 3.5 AU. It just tells us the comet has secrets, layers of them. And we're only seeing the surface. We'll return to this anomaly later, but for now the cyanogen glows in the data, a signature of organic chemistry, a whisper of complexity, a reminder that comets are not simple. They're archives. And 3I Atlas is an archive from another star. For weeks the observations continued. Telescopes around the world tracked 3I Atlas, measuring its brightness, its spectrum, its motion. The data accumulated. The papers began to circulate, preprints uploaded to the archives, the online repository where astronomers share their findings before formal publication. The titles were cautious, technical. Spectroscopic Observations of Interstellar Comet 3I Atlas. Water emission at 3.5 AU, implications for volatile composition. Nickel emission in the coma of 3I Atlas. The language was measured. The conclusions tentative. Further observations are needed. The mechanism remains unclear. Additional study is warranted. This is how science proceeds. Slowly, carefully, peer review, replication, verification. No bold claims, no dramatic announcements, just data, models, hypotheses tested against evidence. But beneath the careful language, there was tension, confusion, frustration, because the data didn't make sense, not yet. Not in a way that fit together into a coherent picture. The water emission was impossible. The nickel anomaly was inexplicable. The cyanogen sequence was suggestive, but ambiguous. Each observation was valid. Each measurement was sound, but they didn't converge. They didn't point to a single explanation. It was like assembling a jigsaw puzzle where the pieces came from different boxes. They fit together, sort of, but the image was fractured, disjointed, incomplete. And then the silence began. Not literal silence. The telescopes kept observing. The data kept flowing. But the public conversation quieted. The preprints slowed. The press releases stopped. Why did nobody notice? Because the story didn't fit the narrative. Interstellar objects are supposed to be exciting, mysterious. When Oumuamua, the first confirmed interstellar visitor, was discovered in 2017, it made headlines worldwide. Its elongated shape sparked speculation. Its unusual acceleration prompted wild theories. Alien spacecraft, solar sails, technology from another star. None of that was true. Oumuamua was almost certainly a shard of a shattered planet, a fragment of ice and rock, accelerated by outgassing too faint to detect directly. But the speculation lingered. The mystery sold. 3I Atlas should have been a bigger story. It's more active, more chemically complex, more anomalous. But it didn't capture the public imagination. Perhaps because it looks like a comet. Familiar. Expected. Or perhaps because the anomalies are too technical. Too subtle. Water emission at 3.5 AU doesn't sound impossible to a non-scientist. It just sounds like comet behavior. But to astronomers, it's a screaming red flag. And yet the silence persisted. No major news outlets picked up the story. No documentaries were commissioned. No viral social media threads dissected the data. The comet remained obscure, known only to specialists, buried in technical papers and observatory bulletins. This is not unusual. Most astronomical discoveries are like this, fascinating to experts, invisible to the public. The universe is full of wonders that never trend on Twitter. Neutron stars with mountains 1 millimeter tall but dense enough to collapse a building. Black holes that sing in gravitational waves at frequencies below human hearing. Galaxies colliding in slow motion over hundreds of millions of years. These phenomena are real, profound, beautiful, and almost no one knows they exist. 3I Atlas joined the ranks of the overlooked. A comet doing the impossible, watched by a handful of observatories, discussed in a handful of papers and otherwise ignored. But the silence was about to break. In late summer, a citizen science project called Radio Home detected something unusual. Radio Home is a distributed computing network. Thousands of volunteers donate spare processing power from their personal computers to analyze radio telescope data. The project searches for transient signals, pulsars and other radio phenomena in the vast archives of the low-frequency array, LOFAR, a radio telescope network spread across Europe. One volunteer's computer flagged an anomaly, a faint, narrow-band radio signal, intermittent, originating from the direction of 3I Atlas. At first it seemed like noise, radio interference, a glitch in the data processing pipeline. Radio astronomy is plagued by interference, satellites, radar, cell phone towers, even electric fences. False positives are common, but this signal was different. It appeared multiple times on different days, always from the same celestial coordinate, and it was narrow-band confined to a specific frequency range, not spread across the spectrum like natural radio emission. Narrow-band signals are rare in nature. Most cosmic radio sources are broadband pulsars, supernova remnants, active galactic nuclei. They emit across wide swaths of the radio spectrum. Narrow-band signals suggest a specific emission mechanism, a resonance, a cavity. And this is where speculation begins a deliberate transmission. The radio home discovery was posted to an online forum. Other volunteers checked their own data. The signal appeared in multiple independent datasets. It was real. Faint, but real. Within days, professional astronomers were alerted. LOFAR re-observed 3I Atlas. The signal appeared again, weak, intermittent, but present. The frequency, 327 megahertz, a wavelength of about 92 centimeters. This is in the so-called waterhole, a quiet region of the radio spectrum between the emission lines of hydrogen and hydroxyl, relatively free of interference, often considered a promising band for interstellar communication. That coincidence sparked conversation. Not wild speculation, not tabloid headlines, but quiet, careful discussion among researchers. Could the signal be artificial? Could it be a beacon, a transmitter? The answer, almost certainly, is no. Natural explanations exist. Plasma waves in the coma, driven by the interaction between the solar wind and the cometary outgassing, can generate radio emission. It's rare, but it's been observed in other comets, particularly active comets, comets with strong ionospheres, but 3I Atlas is not particularly active. 40 kilograms of water per second is impressive at 3.5 AU, but it's modest compared to sun-grazing comets. The density of ions in the coma should be too low to support coherent plasma oscillations, unless the coma is denser than it appears, unless the water emission is concentrated in jets, localized regions of high gas density, or unless the radio emission is not coming from the coma at all, but from the nucleus itself. This is where the speculation edges closer to the uncomfortable. Could there be something inside the nucleus? Not biological, not technological in the human sense, but structured, organized, a cavity, a hollow, a void filled with gas at a specific pressure, resonating at radio frequencies as the nucleus tumbles. It's possible, barely. It requires specific geometry, specific chemistry, specific conditions, too many specifics. Or perhaps the signal is unrelated to the comet. Perhaps it's a background source, a distant galaxy, a pulsar, a radio transient that happens to lie along the same line of sight. Coincidences happen. The sky is full of radio sources. Alignment is not evidence of connection, but the timing is suspicious. The signal appeared after the comet activated. It's intermittent, like the cyanogen emission. It comes from the comet's position, not from a fixed background source. The most honest answer is, we don't know. The signal is real. The connection to the comet is plausible. The explanation is absent. And that uncertainty is itself a kind of signal, a reminder that we're watching something we don't fully understand, something that defies our categories, our models, our expectations. The question hangs in the air, unanswered. What are we really looking at? The discovery of 3I Atlas was not made by human eyes. It was made by an algorithm. The Atlas Survey System Asteroid Terrestrial Impact Last Alert System consists of 4 robotic telescopes stationed in Hawaii and South Africa. Every clear night, they scan the sky, photographing millions of stars, searching for anything that moves or changes. Asteroids, comets, supernovae, anything transient. The telescopes generate terabytes of data every night, far too much for humans to analyze, manually. So the work is done by software. Algorithms compare each new image to reference images from previous nights. Anything that appears, disappears, or moves is flagged. The algorithm ranks the detections by priority: likely asteroids, possible comets, probable noise. 3I Atlas was flagged as a possible comet. The algorithm noted its motion, its faintness, its position far from the ecliptic, the plane where most asteroids orbit. A human astronomer reviewed the detection, confirmed it was real, and submitted the observation to the Minor Planet Center, the central repository for asteroid and comet data. The Minor Planet Center's own algorithms calculated a preliminary orbit, hyperbolic, interstellar. The third confirmed visitor from beyond the solar system. The discovery was announced in a circular electronic bulletin distributed to astronomers worldwide. No press release, no fanfare, just a technical notice, object designation, coordinates, orbital elements, magnitude. Most people never saw it. Most people never will. This is how discovery works now. Not through lone astronomers peering through eyepieces, but through automated systems, machine learning, data pipelines. The sky is too vast, the objects too numerous, the signals too faint. Human attention is a bottleneck. Algorithms scale. But algorithms are also filters. They find what they're programmed to find. They flag what matches their criteria. Anything unusual, truly unusual, unprecedented, outside the training set might be discarded as noise. How many anomalies have we missed? How many objects are out there visible in our data but invisible to our algorithms because they don't look like what we expect? This question haunts every automated survey, the fear that something important is hiding in plain sight, filtered out by software designed to recognize the familiar. 3i Atlas was lucky. It moved, it brightened. It fit the profile of a comet closely enough that the algorithm flagged it. But if it had behaved differently, if it had been inert, or moved more slowly, or appeared in a crowded star field, it might have been missed. And if 3i Atlas is not unique, if there are other interstellar visitors like it, scattered across the sky, how many have we overlooked? The Vera Rubin Observatory, currently under construction in Chile, will change this. Its telescope is massive. Its camera is the largest ever built for astronomy, 0.2 billion pixels. It will photograph the entire visible sky every few nights, generating orders of magnitude more data than any previous survey. And its algorithms will be more sophisticated, trained on larger datasets, tuned to detect fainter, faster, stranger objects. The hope is that Rubin will find hundreds of interstellar visitors per year, perhaps thousands, a population large enough to study statistically, to understand. But Rubin is not operational yet. Its first light is still months away, and in the meantime, we're limited, watching through narrower apertures, missing more than we see. 3i Atlas is a reminder of what's out there, waiting to be noticed. Not just one comet, but a population. Not just one anomaly, but a pattern. The galaxy is full of exiles, and they're passing through all the time. We just need to learn how to see them. By early autumn, the scientific community was divided. Not publicly, not dramatically, but in the quiet spaces where researchers talk, conference hallways, email chains, private Slack channels, the disagreements were sharpening. One camp. This is a natural phenomenon. Unusual, yes, challenging, absolutely, but natural. The water emission can be explained by subsurface heat retention, hypervolatile-driven fracturing, or some combination of thermal and structural effects we haven't fully modeled yet. The nickel anomaly is chemical, not exotic. The radio signal is plasma noise or a background source. Everything has an explanation. We just need better data. The other camp, something is wrong. Not with the observations. The data is sound. But with our assumptions, we're trying to fit 3i Atlas into a framework built for solar system comets. But 3i Atlas is not a solar system comet. It's interstellar. It came from somewhere else. Somewhere with different chemistry, different formation conditions, different physics. We're using the wrong models. We need new ones. Both camps are right. And both are frustrated. The first camp is frustrated because the data doesn't cooperate. Every model they build requires fine-tuning, special conditions, unlikely coincidences. The explanations work technically, but they feel forced, artificial, like trying to explain a square peg by carving the round hole into a square. The second camp is frustrated because they don't have better models. It's easy to say we need new physics. It's hard to propose what that physics might be. What mechanism could produce nickel without iron? What process could sustain water emission at 3.5 AU? The answers are not obvious. And without answers, the frustration turns inward, into speculation, into doubt. This fracture, this split between explain it naturally and admit we don't understand, is not unique to 3i Atlas. It happens in every field when observations outpace theory. In cosmology, when dark matter and dark energy were proposed. In particle physics, when neutrino oscillations were discovered. In exoplanet science, when hot Jupiters were found. The pattern is always the same. First, denial. The observations must be wrong. Then, acceptance. The observations are real. Then, fragmentation. Some researchers cling to existing models, others push for new ones, and in the middle, the majority waits, watches, reserves judgment. 3i Atlas is in this middle phase now. The observations are accepted, the explanations are not. And into this uncertainty, a new question emerged. Why did nobody notice? Not the astronomers. They noticed. They're publishing papers. They're debating interpretations. But the public, the media, the broader scientific community. Why is 3i Atlas not headline news? One answer: it's not visual. There's no dramatic image, no glowing tail arcing across the sky. Just spectral data, numbers, graphs. That doesn't capture attention. Another answer: it's not conclusive. The story doesn't have an ending. The mystery doesn't have a solution. Audiences want resolution. They want answers. Comet behaves strangely. Scientists unsure why is not a satisfying narrative. But there's a darker answer. One that circulates in whispers, in private conversations, in the margins of forums. Perhaps nobody noticed because nobody wanted to notice. Not a conspiracy, not censorship, but something subtler. A collective reluctance to engage with anomalies that don't fit neatly into established categories. A preference for stories that reinforce what we already believe. Comets are ice. Stars are predictable. The universe operates according to known laws, over stories that challenge those beliefs. This reluctance is not malicious, it's human. We filter the world. We prioritize familiar patterns. We dismiss outliers. Because if we didn't, we'd drown in noise, in ambiguity, in questions without answers. But sometimes the outliers matter. Sometimes the noise is signal. And 3i Atlas might be one of those times. The fracture in the scientific community is a reflection of a larger fracture between what we know and what we are seeing, between our models and reality, between confidence and doubt, and that fracture is widening. Let's return to the water. Because the water is the center of this mystery. Everything else, the nickel, the cyanogen, the radio signal, is secondary. Intriguing, but secondary. The water is primary. The water is impossible. 40 kilograms per second, at 3.5 astronomical units, where the sun's warmth is barely a whisper. To understand why this matters, we need to talk about energy, specifically the energy required to sublimate ice. Sublimation is a phase transition, solid to gas. It requires energy heat to break the molecular bonds holding the ice together. For water ice, this energy is called the latent heat of sublimation. It's about 2,800 kilojoules per kilogram. That means every kilogram of water vapor released into space requires 2,800 kilojoules of energy. 40 kilograms per second requires 112,000 kilojoules per second. That's 112 megawatts, the power output of a small power plant. Continuously. Where is that energy coming from? At Earth's distance. From the Sun, 1 Earth solar flux is about 1,360 watts per square meter. Sunlight delivers enough energy to drive vigorous sublimation on a comet nucleus exposed to direct sunlight. At 3.5 AU, the solar flux drops to about 111 watts per square meter. 1/12 the energy. Not enough, not even close. Even if the entire sunlit hemisphere of the nucleus were sublimating every square meter, releasing water vapor, the energy budget doesn't balance. The nucleus of 3i Atlas is estimated to be a few kilometers across. Let's say 2 kilometers. The sunlit cross-section is roughly 3 square kilometers, or 3 million square meters. At 111 watts per square meter, the total solar energy absorbed is about 333 megawatts. That sounds like enough. But it's not, because most of that energy is reflected or radiated away as infrared heat. Only a fraction goes into sublimation, and that fraction is not enough to account for 40 kilograms per second of water. The models fail. The energy doesn't add up. The water shouldn't be there. And yet it is. One possibility. Thermal inertia. Perhaps the nucleus is not in thermal equilibrium. Perhaps it absorbed heat when it was closer to another star, its home star. Wherever that is, and it's releasing that stored heat now, slowly, over millions of years. Like a brick pulled from a fire, cooling gradually, staying warm long after the fire is out. But comets are not bricks. They're porous, fluffy, made of ice and dust loosely bound together. They don't retain heat well. They cool quickly. Any heat absorbed billions of years ago when the comet formed should be long gone, unless the interior is different, denser, more compact, thermally insulated by layers of dust or refractory crust, a core that stays warm while the surface freezes. This is speculative. It requires specific structure, specific composition. It's possible, but not simple. Another possibility, chemical energy. Perhaps the nucleus contains reactive materials, organic compounds, metals, peroxides that release heat when exposed to vacuum or sunlight. Exothermic reactions. The heat drives sublimation. The sublimation exposes more reactive material. The process feeds itself. This is also speculative, but it's testable. If chemical reactions are driving the activity, the spectrum should show unusual molecules. Reaction products. Oxidation states that don't match equilibrium chemistry. No such signals have been detected yet, but that doesn't mean they're absent. Spectroscopy has limits. Faint signals can be missed. The water remains unexplained. A fountain in the wasteland. A violation of the rules. And the more we study it, the less sense it makes. Think of it this way. Imagine finding a river in the middle of a desert. No rain, no snowmelt, no aquifer. Just water flowing endlessly from no visible source. You measure the flow. You analyze the water. It's real. But the source is invisible, hidden, impossible. That's 3I Atlas, a river with no source. Water from nowhere. And that's what keeps astronomers up at night. If 3I Atlas originated in the galactic thick disk, that origin changes everything. The thick disk is not a place. It's a population, a collection of stars older, more metal-rich, and more dispersed than the stars of the thin disk, the flat, spiral-armed plane where our sun resides. Thick disk stars orbit the galactic center in tilted, elongated paths, plunging above and below the plane, crossing through different regions of the galaxy over their lifetimes. These stars are ancient, 7 billion years old, 8 billion. Some may be 10 billion years old, nearly as old as the galaxy itself, formed when the Milky Way was young and chaotic, still assembling from the merger of smaller galaxies. If 3I Atlas came from a thick disk star system, it's a relic, a fossil from the early galaxy. It formed in a protoplanetary disk around a star that has since evolved, aged, perhaps died. The chemistry of that disk may have been different from ours. The elemental abundances, the dust composition, the volatile inventory. This could explain the nickel anomaly. Thick disk stars are enriched in heavy elements metals in astronomical parlance because they formed from gas polluted by earlier generations of supernovae. But the specific ratios of elements can vary. A supernova that explodes asymmetrically, ejecting nickel-rich ejecta in one direction and iron-rich ejecta in another, could create pockets of gas with unusual elemental abundances. A comet forming in such a pocket would inherit that chemistry. It's speculative, but it's not implausible. The thick disk origin also raises a deeper question. How many other objects like 3I Atlas are out there? If one thick disk comet can wander into our solar system, there must be more. Many more. Thick disk stars are common. About 10% of the stars in the solar neighborhood belong to the thick disk. If even a fraction of those stars have comet populations, and if even a fraction of those comets are ejected into interstellar space, the galaxy should be teeming with ancient, wandering ice balls. We've found 3 interstellar objects so far: Oumuamua, 2I Borisov, 3I Atlas. 3 in 8 years. That's a detection rate. From that rate, astronomers can estimate the population. The math is rough, but the numbers are staggering. For every interstellar object we detect, thousands must pass through the solar system unnoticed, too faint, too fast, too small, or simply pointing in the wrong direction when we happen to look. Extrapolating to the galaxy as a whole, there could be trillions of interstellar comets wandering the Milky Way at any given time. Trillions. A vast, invisible population, a galactic swarm of icy exiles drifting through the dark, occasionally passing through stellar systems like ours, briefly illuminated, briefly observed, then gone. 3I Atlas is one droplet in that ocean, one voice in a cosmic chorus we're only beginning to hear. And if thick-disk comets are common, their chemistry matters, because thick-disk stars are the progenitors of the thin disk. The Milky Way we see today, the spiral arms, the star-forming regions, the Sun and its planets grew out of the thick disk. The material was recycled. Gas expelled from dying thick-disk stars enriched the interstellar medium, which collapsed into new stars, new disks, new planets. If thick-disk comets carry unusual chemistry, nickel without iron, high CO2, organic layers, that chemistry was part of the galactic inheritance, part of the raw material that built our solar system, part of us. We are made of stardust, yes, but we're also made of thick disk dust, ancient, recycled, chemically complex. 3I Atlas is a messenger from that ancient past, a fragment of galactic memory, carrying information about conditions we can never observe directly. And the more we study it, the more we realize we're not just looking at a comet, we're looking at history. Amateur astronomers are watching 3I Atlas. Not many. The comet is faint magnitude 18, near the limit of visibility for backyard telescopes, but a dedicated few are tracking it, imaging it, measuring its brightness, contributing observations to public databases. This is citizen science in its purest form, not organized campaigns, not crowdsourced data analysis, just individuals with telescopes, taking pictures, sharing data, participating in the collective effort to understand the universe. One amateur astronomer in New Zealand captured a sequence of images showing the comet's coma flickering, brightening and dimming over the course of a few hours, not periodically, erratically, as if the outgassing were pulsing, unsteady, chaotic. Professional astronomers requested the images, analyzed them. The flickering was real, confirmed by other observers, unexplained. Comets can flicker due to rotation. If the nucleus is irregularly shaped, with active regions concentrated on one hemisphere, the brightness varies as the nucleus spins, a lighthouse effect. But the flickering of 3I Atlas doesn't match a rotational pattern. It's too irregular, too fast. Perhaps the flickering is caused by jets, narrow beams of gas and dust erupting from specific vents on the nucleus. As the jets switch on and off, triggered by thermal cycling, structural shifts or subsurface pressure changes, the brightness varies. This is seen in some active comets, particularly those undergoing outbursts. But 3I Atlas is not undergoing an outburst. Not in the traditional sense. The activity is sustained, persistent. The flickering is a modulation on top of that baseline, a variation within the anomaly. It's as if the comet is breathing, not metaphorically, not poetically, but physically, inhaling and exhaling, expanding and contracting, alive in some mechanical thermodynamic sense. This is dangerous language. Alive implies biology, metabolism, intent. None of those apply. 3I Atlas is not alive. It's a rock, ice, dust. It doesn't think. It doesn't choose. It obeys physics. And yet the metaphor lingers, because the behavior is so unlike anything we expect from an inert object. The flickering, the sustained activity, the chemical complexity, the radio signal. Taken together, they create an impression of feeling, not a fact that something more is happening. This is where science edges into psychology, where observation blurs into interpretation, where data becomes narrative. Astronomers are trained to resist this, to separate signal from story, to focus on measurements, not meanings. But humans are storytelling animals. We see patterns, we infer intention, we project life onto the lifeless. The moon has a face, constellations have shapes. Pareidolia, the tendency to see faces in random patterns, is hardwired into our brains. It's an evolutionary adaptation. Better to mistake a shadow for a predator than to miss a predator in the shadows. We do the same with data. We see patterns that might not be there. We infer structure from noise. We tell ourselves stories about comets that breathe and signals from nowhere. Most of the time the stories are wrong. The patterns are illusions. The pareidolia is just pareidolia. But sometimes, rarely, but sometimes, the patterns are real. The structure is there, the story is true. How do we know which is which? We don't. Not yet. Not until we have more data, more observations, more time. And that's the tension at the heart of this mystery. The line between discovery and delusion, between seeing what's there and seeing what we want to be there. 3i Atlas walks that line, and so do we. Oumuamua, 2i Borisov, 3i Atlas. 3 confirmed interstellar visitors, 3 points in a growing catalogue. Oumuamua was the first. Discovered in October 2017, it was unlike anything seen before. Elongated, tumbling, accelerating as it left the inner solar system, pushed by some unseen force. The acceleration sparked speculation alien spacecraft, solar sails, hydrogen icebergs. None of the explanations were entirely satisfying. Oumuamua remains a mystery, already too far and too faint to observe, its nature forever ambiguous. 2i Borisov was the second. Discovered in August 2019, it was refreshingly normal. A comet, fuzzy, active. Its spectrum matched solar system comets. Its composition was familiar: carbon monoxide, water, dust. Borisov was a relief, a confirmation that interstellar objects can be ordinary, that not everything from beyond is strange. 3i Atlas is the third, and it's strange again. 3 objects, 3 behaviors. Oumuamua, anomalous. Borisov, normal. Atlas, impossible. What does this tell us? That interstellar objects are diverse, that we can't generalize from a sample of 3, that the galaxy is full of surprises. But it also tells us something deeper. It tells us that our solar system is not isolated, it's porous, permeable. Objects enter all the time. Most pass through unnoticed, too small, too faint, too fast. But some are large enough, bright enough, active enough to be detected. And if 3 have been detected in 8 years, how many have passed through undetected in Earth's history? Millions. Tens of millions. Interstellar visitors have been entering the solar system for 4.5 billion years. Some may have collided with planets. Some may have delivered water to Earth. Some may have seeded the early solar system with organic molecules, contributing to the chemistry that led to life. We don't know. We can't know. The past is invisible, but the present is observable. And the Vera Rubin Observatory will change what we see. Rubin will detect hundreds of interstellar objects per year, perhaps thousands, a population large enough to study statistically, to categorize, to understand. We'll learn which types of objects are common, which are rare. We'll measure their size distribution, their velocity distribution, their compositional diversity. We'll be able to ask, are most interstellar comets like Borisov ordinary, familiar? Or are they like Oumuamua and Atlas strange, anomalous, defying expectations? And we'll begin to map the galaxy in a new way, not by observing distant stars, but by studying the debris those stars eject. Every interstellar visitor carries information about its birthplace, its chemistry, its history. A comet from a metal-poor star will look different from a comet from a metal-rich star. A comet from a young, massive star will differ from a comet from an old, dying star. The gallery of exiles will become a library, a collection of samples from across the galaxy, delivered to us free of charge for study. 3i Atlas is one volume in that library, one data point, one story, incomplete, ambiguous, frustrating, but real. And the more we read, the more we'll understand not just about comets, but about the galaxy itself, about the diversity of star systems, about the chemistry of planet formation, about the conditions that lead to life. We're just beginning to read. Here's the uncomfortable question. Is 3i Atlas a mirror? Not a literal mirror, but a reflection, a projection, an object onto which we cast our hopes, our fears, our desires for meaning. Humans have done this for millennia. We've looked at the stars and seen gods, looked at comets and seen omens, looked at eclipses and seen wrath. The sky has always been a canvas for human imagination, a place where we project our stories. Modern science was supposed to change that, to strip away the mythology, to see the universe as it is, material, mechanical, indifferent. Stars are not gods. Comets are not omens. Eclipses are geometry. And yet, the impulse remains. When we encounter something strange, something anomalous, something that doesn't fit, we reach for stories. Alien technology, hidden civilizations, messages from the cosmos. We did this with Oumuamua. Its elongated shape became a spaceship. Its acceleration became propulsion. The fact that we didn't fully understand it became evidence of intelligence. None of that was true. Oumuamua is almost certainly natural, but the speculation persisted because the alternative, we don't understand it yet, is unsatisfying. It leaves the mystery open, and humans don't like open mysteries. Are we doing the same with 3i Atlas, seeing patterns that aren't there, inferring intention where there's only physics? The answer is probably, to some extent, inevitably. But that doesn't mean the anomalies are not real. The water emission is real. The nickel is real. The radio signal is real. The flickering is real. These are observations, not interpretations. The question is what we do with those observations. Do we force them into existing models, no matter how awkward the fit? Or do we admit ignorance, hold the mystery open, and wait for better data? Both approaches are valid. Both are necessary. Science progresses through a tension between explanation and exploration, between closing questions and opening new ones. 3i Atlas sits at that intersection. It challenges us, not just intellectually but emotionally, because it reminds us how little we know, how much remains hidden, how vast and strange the universe is. And perhaps that's the real lesson. Not that comets are alive, or that aliens are sending signals, or that the universe is watching us back, but that we humans, observers, storytellers are part of the mystery. Our confusion is part of the data. Our questions are part of the phenomenon. We're not separate from the cosmos. We're embedded in it, made of it, shaped by it. And when we look at 3i Atlas, we're not just looking at a comet. We're looking at ourselves, at our limits, at our capacity for wonder and frustration in equal measure. The comet is a mirror, and what we see in it says as much about us as it does about the universe. But the question remains, what if the mirror is looking back? Let's go back to physics, because speculation without constraints is just fiction, and the constraints here are real. The energy problem has not been solved. 40 kilograms of water per second requires energy, lots of it, and that energy has to come from somewhere. We've ruled out sunlight, not enough, not at 3.5 AU. Even with perfect absorption, perfect efficiency, the numbers don't add up. We've considered stored heat, but comets don't retain heat, they cool quickly. Any thermal energy absorbed billions of years ago is long gone. We've speculated about chemical reactions, exothermic processes, reactive materials in the nucleus. But the spectroscopy doesn't show unusual oxidation states or reaction products. So where is the energy? One possibility we haven't fully explored, radioactivity. Comets are not radioactive, not significantly. They contain trace amounts of uranium, thorium, potassium-40, the usual suspects. But the concentrations are low. The heat output is negligible, not enough to warm the surface, let alone drive water sublimation. But what if 3i Atlas is different? What if it formed in a region, enriched in radioactive isotopes? A molecular cloud near a recent supernova, perhaps, contaminated by fresh ejecta containing short-lived radioisotopes, aluminum-26, iron-60, calcium-41. These isotopes decay quickly, releasing heat. If the comet's nucleus contains even small amounts, the cumulative heat could be significant. It's possible. But there's a problem. Short-lived isotopes decay. Aluminum-26 has a half-life of 717,000 years. Iron-60 has a half-life of 2.6 million years. If 3I Atlas is billions of years old, if it came from the thick disk, those isotopes are long gone, decayed into stable elements, inert. Unless the comet is young, much younger than we think, formed not billions of years ago, but millions, or even less. This raises a bizarre question. Could 3I Atlas be a recently formed comet, ejected from a young stellar system? A system still in its planet-building phase, where collisions are common, where planetesimals are scattered outward by gravitational encounters with giant planets. It's possible. Young stars eject material all the time. If 3I Atlas formed around a star only a few million years old and was ejected shortly after, it could still retain short-lived radioisotopes. The internal heat from radioactive decay could sustain water sublimation at 3.5 AU, but this contradicts the thick disk origin. Thick disk stars are old. Their planet-forming days are long past. If 3I Atlas came from the thick disk, it can't be young, unless it didn't come from the thick disk at all, unless the trajectory is misleading, unless the comet's true origin is elsewhere, a young star cluster, a star-forming region, someplace we haven't considered. The energy problem is a knot. Every solution creates a new contradiction. Every explanation requires unlikely coincidences. Perhaps the answer is simpler. Perhaps we're missing something obvious, a physical process we haven't thought of, a mechanism operating at small scales, molecular, atomic, that becomes significant in aggregate. Or perhaps the answer is that there is no single explanation. Perhaps 3I Atlas is a confluence of factors. Radioactivity plus chemical energy plus thermal inertia plus structural instability. A perfect storm of conditions that align just right to produce the observed behavior. But perfect storms are rare, unlikely. And that unlikeliness is itself a clue, because if 3I Atlas is unique, if no other comet behaves this way, then it's an outlier, a freak, an accident. But if it's not unique, if other interstellar comets show similar behavior, then it's a pattern, a population, something real. We don't know yet. We have a sample size of 1, and from 1 you can't infer a pattern. But the energy problem remains, unsolved, waiting. And that's what keeps astronomers up at night. The low-frequency array LOFARIS, not a telescope, it's a network. Thousands of small antennas scattered across Europe, linked by fiber optics, operating as a single instrument. It listens to the universe at low radio. Frequencies, wavelengths measured in meters, not centimeters. These are the longest radio waves accessible from Earth's surface, just below the cutoff imposed by the ionosphere. At these frequencies, the universe sounds different. Pulsars emit sharp pulses. Jupiter roars with plasma oscillations. Supernova remnants glow with synchrotron radiation, and occasionally, very occasionally, something unexpected appears. The radio signal from 3I Atlas was detected by LOFAR in late summer. Faint, intermittent, narrowband, 327 MHz, a wavelength of 92 centimeters. Follow-up observations confirmed it. The signal appeared multiple times, always from the comet's position. It wasn't background noise, it wasn't interference, it was real. But what produces a narrowband radio signal from a comet? One possibility: coherent plasma oscillations. When the solar wind stream of charged particles flowing outward from the sun encounters the comet's coma, it interacts with ions in the gas. The interaction can generate plasma waves, oscillations in the electron density, which emit radio waves at specific frequencies determined by the plasma density. This is rare, but it's been observed. Comets Halley and Hyakutake emitted radio waves during close solar approaches when their comae were dense and highly ionized. But 3I Atlas is not close to the sun. Its coma is not particularly dense. The conditions for plasma oscillations shouldn't be met, unless the coma is denser than it appears, unless the water emission is concentrated in jets, creating localized pockets of high ion density, or unless the solar wind at 3.5 AU is more turbulent than expected, enhancing the interaction. These are possibilities, not explanations, not yet. Another possibility: the signal is not coming from the coma at all. It's coming from the nucleus, or more precisely, from within the nucleus. Imagine a cavity, a void inside the comet filled with gas at a specific pressure. As the nucleus tumbles, the cavity resonates, like blowing across the mouth of a bottle. The resonance frequency depends on the cavity's size and shape, and the gas pressure. If the conditions are right, the resonance could emit radio waves. This is speculative, wildly so. It requires a hollow comet, a nucleus that's not solid but porous, fragmented, held together by weak gravity, like a rubble pile, but with gaps large enough to form acoustic cavities. It's not impossible. Some asteroids are rubble piles, loose aggregates of rock and dust, barely held together, with voids and cavities throughout. If 3I Atlas is similar, if it's a pile of icy fragments rather than a solid nucleus, then cavities could exist. But acoustic resonances emit sound waves, not radio waves. To emit radio, you need charged particles, plasma, or something else. This is where the speculation becomes uncomfortable, because the something else could be almost anything. Piezoelectric materials, crystalline structures, magnetic fields. Even though it feels absurd to write something organized, not alive, not technological, but structured, ordered, geometric. This is the edge of science, the place where hypotheses become wild guesses, where data stops and imagination begins. The radio signal is real, the explanation is not. Lofar continues to observe. The signal appears intermittently, sometimes strong, sometimes absent. No clear pattern, no periodicity, just noise that might be signal or signal that might be noise. And the ambiguity persists. The square kilometer array SKI is not finished yet, but when it is, it will be the most powerful radio telescope ever built. A network of antennas spread across Australia and South Africa, with a combined collecting area of 1 square kilometer. Hence the name. SKA will detect signals 1,000 times fainter than current instruments. It will map the radio sky in unprecedented detail. It will listen to the universe in frequencies we've barely explored. And it will observe interstellar objects like 3I Atlas with precision we can only dream of now. When SKA becomes operational, currently projected for the late 2020s, we'll be able to detect radio signals from comets at vast distances, not just in our solar system, but potentially from comets passing through nearby star systems. It will measure plasma densities, magnetic fields, chemical compositions. It will test hypotheses about coherent emission, cavity resonances, and whatever else might produce narrowband signals. And it will answer the question: is 3I Atlas unique, or is it part of a population? If other interstellar comets emit similar radio signals, SKA will find them. If those signals follow patterns, correlations with outgassing, with rotation, with solar distance, SKA will measure them. And slowly, painstakingly, we'll build a picture of what's normal and what's anomalous. But SKA is not operational yet, and 3I Atlas will be gone by then. Already the comet is fading, moving farther from the sun, cooling, dimming. Within a year, it will be too faint for most telescopes to observe. Within 2 years, it will vanish entirely, lost in the depths of space. This is the tragedy of interstellar objects. They arrive unannounced. We scramble to observe them. We extract every photon we can, and then they leave, carrying their secrets with them before we've had time to fully understand. It's like meeting a traveler on a road. You have a brief conversation. You learn fragments of their story, where they've been, what they've seen. But before you can ask the important questions, they're gone. And you're left wondering, what did I miss? What didn't they tell me? Will I ever see them again? The answer is almost certainly no. Space is vast. The galaxy is enormous. The odds of encountering the same interstellar object twice are infinitesimal. 3i Atlas will leave, and we'll never know what it really was, unless it's not unique, unless there are others like it, approaching even now, waiting to be discovered. If interstellar comets with strange chemistry and anomalous behavior are common, we'll encounter more. We'll refine our observations. We'll build better models. We'll learn. But if 3i Atlas is one of a kind of freak, an accident, a perfect storm, then this may be our only chance. And we're running out of time. The Vera Rubin Observatory will help. SKA will help. Future mission spacecraft designed to intercept interstellar objects, to rendezvous with them, to study them up close, will help even more. But those are years away, decades away. For now we have telescopes on Earth limited by atmosphere and distance. We have 3i Atlas fading in the outer solar system. And we have questions, so many questions. But the question remains, will we answer them in time? By mid-autumn, something strange was happening, not with the comet, with the conversation around it. The papers continued to be published. The observations continued. The data accumulated. But the discussion, the public discussion, the online forums, the social media threads began to quiet. Not because interest waned, but because the mystery refused to resolve. People want answers. They want closure. They want the story to end with understanding. Scientists were baffled, but then they figured it out. That's the narrative, that's the expectation. But 3i Atlas didn't cooperate. The anomalies persisted, the explanations remained tentative, the energy problem unsolved, the nickel unexplained, the radio signal ambiguous. And so the silence grew. Not the silence of forgetting, but the silence of waiting, of watching, of uncertainty. This is a strange phenomenon. In the age of instant information, of viral stories, of attention measured in hours, prolonged ambiguity is uncomfortable. We're accustomed to resolution, to answers, to knowing. 3i Atlas offers no resolution, only questions, and questions without answers fade from view. This is not unique to comets. It happens in every field. Dark matter, unexplained for decades. Dark energy, discovered 25 years ago, still mysterious. Fast radio bursts, detected for over a decade, origins still debated. These phenomena are real, profound, important, and almost invisible in popular consciousness because they don't offer satisfying stories. They offer mysteries, and mysteries that don't resolve become background noise. But the silence around 3i Atlas feels different, because this isn't an abstract cosmological puzzle. This is a physical object moving through our solar system, observable, real, something we could in principle reach, touch, study, and yet we're letting it slip away, not deliberately, not through neglect, but through the simple passage of time. The comet is leaving, the observations are ending, the window is closing, and the silence becomes louder than any announcement. Perhaps that's the real anomaly. Not the comet's behavior, but ours. The way we engage with mysteries. The way we demand answers before we've asked all the questions. The way we move on when the story doesn't satisfy. 3i Atlas will be forgotten. Not by astronomers, they'll remember, analyze the data for years, revisit the observations when new tools become available. But by everyone else. The comet will vanish from conversation, from memory, from the collective awareness, until perhaps another arrives, another interstellar visitor with strange chemistry and impossible behavior. And then we'll remember, we'll compare, we'll wonder, was 3i Atlas the beginning of a pattern or an outlier we'll never see again? We don't know. And that not knowing is the hardest part. Because silence is not the absence of signal. Sometimes it's the signal itself, the universe telling us, you're not ready. You don't have the tools. You don't have the framework. Wait, watch, learn. And so we wait. But the question remains, what are we waiting for? Out there right now, other comets are approaching. We don't see them. They're too faint, too distant, moving through the outer solar system or beyond, invisible to current telescopes. But they're there. Statistically, They must be. If 3 interstellar objects have been detected in 8 years, hundreds must have passed through unnoticed. And if hundreds have passed through, thousands more are currently in transit, somewhere in the space between stars. This is the unseen population, a vast, invisible swarm of interstellar debris wandering the galaxy, occasionally intersecting stellar systems like ours. Most are small, asteroid-sized, comet-sized, too small to shape the dynamics of star systems, but large enough to carry information, chemistry, history, stories written in ice and rock. Some are larger, planet-sized perhaps, rogue planets, ejected from their birth systems, drifting alone through the dark. These are even harder to detect. They don't reflect much light. They don't emit heat. They're ghosts, but simulations suggest they're common. For every star in the galaxy, there may be one or more. Rogue planets, billions of wandering worlds, homeless, lightless, invisible. And some may be smaller than we've considered. Dust grains, molecules, atoms, interstellar wind. Not objects exactly, but material. A continuous flow of galactic matter, passing through the solar system all the time. Mixing with our own dust and gas, indistinguishable from the background. We live in a permeable system. The solar system has no walls, no boundaries. Objects enter, objects leave. Material flows in and out. We're not isolated. We're embedded in the galaxy, connected. 3i Atlas is one visible node in that network, one messenger, one data point. But it represents a larger reality. The galaxy is alive with motion, with debris, with travelers, and we're just beginning to see them. The Vera Rubin Observatory will change the count, from 3 detected objects to hundreds per year, perhaps thousands. The population will come into focus. We'll measure size distributions, velocity distributions, compositional diversity. We'll learn what's typical, what's rare, whether 3i Atlas is an outlier or a preview of things to come, and we'll begin to ask new questions, not just, what is this object, but what does the population tell us about the galaxy, about star formation, about planetary system architectures, about the ejection mechanisms that send comets into interstellar space. Because every interstellar object is a refugee, something expelled, cast out, sent into exile by gravitational interactions, stellar encounters, planetary collisions. Their presence tells us about violence, about instability, about the chaotic processes that sculpt stellar systems. Our solar system has ejected objects too, comets scattered by Jupiter's gravity, flung outward, escaping the sun's pull, becoming interstellar travelers themselves. Somewhere in the galaxy right now, a solar system comet is passing through another star's planetary system, observed by astronomers who wonder where it came from. We're part of this exchange, not passive recipients but participants, senders and receivers, embedded in the galactic network, and the more we see, the more we'll understand. The galaxy is not empty space punctuated by stars. It's a continuum, a web, a system where everything connects, where nothing is truly isolated. 3i Atlas is a thread in that web, one strand, one connection, and by studying it, we're not just learning about a comet. We're learning about the galaxy, about interconnection, about the way matter and motion and history flow through space, linking stars and systems and time. The unseen population is vast, and we're only beginning to see. So what does 3i Atlas tell us about us? Not about the comet, not about the galaxy, but about ourselves, about humans, about the way we think, the way we see, the way we respond to mystery. We've spent 20 chapters examining a comet, dissecting its anomalies, proposing explanations, speculating about origins. And through it all, a pattern has emerged not in the data, but in our response to it. We want answers. We crave resolution. When faced with ambiguity, we reach for stories natural or artificial, ordinary or extraordinary. We fill the gaps. We smooth over the contradictions. We construct narratives that feel satisfying, even when the evidence is incomplete. This is not a flaw. It's human. We're pattern-recognizing animals. We evolved in environments where seeing patterns, even false ones, was better than missing real ones. The rustling in the grass might be wind, or it might be a predator. Better to assume predator and be wrong than to assume wind and be eaten. We do the same with data. We see signals in noise. We infer structure from randomness. We tell ourselves stories about comets that breathe and signals that might mean something. Most of the time the stories are wrong. The patterns are illusions. Pareidolia, apophenia, the human brain imposing order on chaos. But sometimes, rarely, but sometimes, the patterns are real. And that's the tension, that's the challenge. How do we distinguish between the two? How do we stay open to genuine anomalies without drowning in false positives? There's no algorithm for this, no formula. It requires judgment, experience, skepticism balanced with curiosity, the willingness to say, I don't know, and sit with that uncertainty. 3i Atlas is a test, not of our instruments, not of our models, but of our patience, our humility, our ability to hold mystery without collapsing it prematurely into explanation. And we're failing. Not completely, not catastrophically, but partially. Because we're uncomfortable with ambiguity. We want the comet to be natural or artificial, ordinary or extraordinary. We want it to fit into categories. We want closure. But the universe doesn't care what we want. It is what it is. And sometimes, often what it is ambiguous. 3i Atlas might be a natural comet with unusual chemistry. It might be an outlier, a freak, a confluence of unlikely conditions that produce the observed behavior. Or it might be the first glimpse of something deeper, a population of ancient, chemically strange comets from the thick disk, or from other galaxies, or from conditions we haven't yet imagined. We don't know. And admitting that, sitting with that uncertainty, resisting the urge to force resolution is itself a form of progress. Because the alternative is worse. Premature certainty, false explanations, stories that feel satisfying but don't match reality. Better to wait, to watch, to gather more data, to let the mystery breathe. And perhaps that's the real lesson. Not that comets are breathing, but that we should breathe too. Slow down. Observe. Hold space for ambiguity. Trust that understanding will come in time if we're patient. 3i Atlas is not the answer. It's the question. And the question is, can we live with not knowing? Because the universe is full of things we don't understand. And if we demand answers before we're ready, we'll invent them. We'll fill the gaps with stories. And the stories will be wrong. Better to sit in the dark. To let the mystery remain mysterious. To admit, humbly, that we're watching something we don't yet comprehend. And maybe, just maybe, that's enough. The comet is leaving. Right now, as you read this, 3i Atlas is moving outward, away from the Sun, beyond the orbit of Jupiter, into the deep outer solar system. The water emission is slowing. The coma is fading. Within weeks, it will be too faint for most telescopes to observe. Within months, it will be invisible, and eventually it will cross the boundary. The heliopause, the edge of the solar system, where the solar wind gives way to interstellar space. It will leave, and it will never return. We had a few months to study it, a handful of observations, a few hundred spectral lines, a scatter of radio detections, that's all. And from that, we tried to understand a visitor from another star, carrying chemistry we've never seen, behaving in ways we can't explain. We failed. Not completely. We learned things, we measured things, we ruled out explanations. But we didn't solve it. The mystery remains. And maybe that's okay, because the comet was never the point. The comet is ice and rock, molecules and dust. It doesn't care whether we understand it. It doesn't need explanation. It just is. We're the ones who need understanding. We're the ones who impose meaning, who ask questions, who feel wonder and frustration and awe. The comet is not alive, but we are. And that aliveness, the curiosity, the confusion, the refusal to look away from mystery, that's what matters. Not the comet's chemistry, not its origin, not its trajectory, but the fact that we looked, that we noticed, that we tried. For billions of years, comets have been passing through the solar system. Interstellar visitors, wandering in from the dark, moving through, leaving again, unobserved, uncatalogued, unremarked. But now, for the first time in history, we're watching, we're measuring, we're asking questions. That's new, that's extraordinary, not the comets, us. We're a young species, barely out of the cradle. We've been studying the sky systematically for a few centuries. We've had space telescopes for decades. We've detected interstellar objects for less than a decade. We're beginners, amateurs, students of a universe we've barely begun to comprehend. And yet here we are, building telescopes, writing algorithms, launching satellites, tracking comets, asking questions that have no easy answers, sitting with mysteries that may never resolve. That's what it means to be human, not to have answers, but to ask, to wonder, to reach toward understanding, even when understanding slips away. 3i Atlas will leave, but we'll stay, and we'll watch for the next visitor, and the next, and slowly, painfully, incrementally, we'll learn, not just about comets, but about the galaxy, about ourselves, about what it means to be alive in a universe full of mystery. The comet is not breathing, we are. And as long as we keep breathing, keep watching, keep questioning, keep reaching, the mystery doesn't have to end. It just has to continue. Out here, sunlight is only a whisper. But we're listening, and that's enough.